Hello and welcome to this third data collection and pre-processing lecture in this course, Master in Artificial Intelligence. So in this lecture, we will continue to talk about how to gather relevant data from various sources, ensure its quality, and pre-process it to make it suitable for analysis and modeling. Now, we have talked about scaling and normalization in the previous lectures, and in this we'll talk about feature extraction, which means basically extracting relevant information from the text, images, or other unstructured data using such techniques as TF-IDF, term frequency, inverse document frequency, word embeddings, and image feature extraction algorithms. So let's take a look at first two in this lecture, and then we will talk about in the next lecture about image feature extraction algorithms. So the TF-IDF, standing for term frequency, inverse document frequency, is a technique used in natural language processing, NLP, and information retrieval to quantify the importance of a term, that is a word, a term in the document relative to the collection of the document. TF-IDF is commonly used for feature extraction in text data, uh, for tasks such as document classification, information retrieval, and text mining, right? So let's take a look at how is TF-IDF used for feature extraction, extracting such features from the text data. See, first thing you do is you calculate term frequency. Now, term frequency measures the frequency of a term or a word within a document. It is calculated as number of times a term appears in the Word document divided by the total number of terms in the document, right? So the term frequency is typically normalized to prevent biases towards large data, and you can see the formula for TF reproduced in front of you, right? Then you calculate the inverse document frequency or IDF. Now IDF measures the rarity of the term across a collection of documents. It is calculated as logarithm of the ratio of the total number of documents in the collection to the number of documents containing the term, as you see in the formula here. The IDF score naturally increases with the rarity of the term across the document collection. And you see the formula here, right? Which is IDF is equal to log total number of documents in collection divided by number of documents containing the term. Then you compute TF-IDF score. The TF-IDF scores combine the term frequency, inverse document frequency to compute a numerical score that represents the importance of a term in the document relative to the entire document collection. It is calculated as the product of the term frequency TF and the inverse document frequency IDF, and you see the formula here represented, right? Then the TF-IDF scores are computed for each term as illustrated here. There is a two documents and there are many terms. So the TF-IDF score there represents is calculated for each term in each document in the document collection. Now these scores serves as the feature that represents the importance of each term in each document, right? So on a scale of whatever that is, on information technology, it is 0.77 in the first document, whereas in the second term it is 0. Now resulting TF-IDF metrics that you see here is typically sparse. There are not many data in every row and column, which rows representing documents and column representing terms and values representing TF-IDF scores. This TF-IDF matrix then can be used as an input for the machine learning algorithm for various tasks such as document classification, clustering, or information retrieval. The TF-IDF in summary is used for feature extraction in text data for quantifying the importance of the terms in documents relative to the collection of all the documents. It identifies the important terms that are both frequent within the individual document, high term frequency, and rare across entire document collection, high inverse document frequency, making it a valuable technique for representing text data in machine learning applications, right? Then there's the second thing that is for text data, extraction is word embedding. Now, what are word embeddings? So, word embeddings are dense, low-dimensional vectors, right? Representation of the words in a continuous vector space. Now, they capture semantic and syntactic similarities between based on their distributional property in a large corpus of text data. So basically, semantic and syntactic similarities basically convey semantic is meaning and syntactic is how they are pronounced or they appear while pronouncing. Now, word embeddings are learned using unsupervised learning techniques such as neural network based model like word2vec, GloVec, and FastText. Let's look at an example here. Suppose we have a small corpus of text document consisting of three, sentences. The cat sat on the mat, the dog played in the park, and the bird sang in the tree. To create word embedding, we can use the word to vec algorithm, which learns distributed representation of the words based on their co-occurrence pattern in this corpus of three sentences. After training the word to vec model, each word in the vocabulary is represented by a dense vector in a continuous vector space. And here you see all highlighted. These are the word embeddings or the dense vector in the continuous vector space. So what do these numbers mean in the word embedding? So these numbers like 0 highlighted here 0.2 minus 0.4 and 0, what do these represent really? So each element in the vector, the bracket, the rate numbers, captures a semantic references which conveys its meaning or aspect of a word's meaning. So it's all about meaning one. For example, in word embedding trained in a large text corpus, next set of data, the first element 0.2 might represent a word's association with certain concept on text, while the second element minus 0.4 might represent its syntactic value. How does it sound? Or grammatical property. And the third element 0.1 might represent its relationship to other words in the vocabulary. So that's what these numbers mean in the word embeddings. Now, how are the word embeddings used in feature extraction? Now, let's say that we want to classify these sentences into two categories, animals and nature related. These three sentences, right? The cat sat in the mat, the dog played in the park, and the bird sang in the tree. We can use the word embedding as features for this classification, and that is how it is done. Let's take a look at that. So, for each sentence in the corpus that we have, we represent it by a vector by averaging the word embeddings of all the words in the sentence. For example, in sentence 1, average of the word embeddings for the cat sat on the mat would be the sentence word embedding. Similarly for sentence 2, average of word embeddings for the cat played in the park would be the sentence 3, and so on and so forth for the sentence 3. Once having done that, then we each sentence is now represented. We do feature extraction where each sentence is now represented as a fixed length vector in the same continuous vector space as the word meaning. So we have now correlation. Now these sentence vectors serve as input feature for our classification model. So we have data that we can feed into the classification model. We can use these sentence vectors as features to train the machine learning model like logistic regression, support vector machine, neural network, etc. for text classification. The model learns to classify sentences into predefined categories based on their semantic content captured in the word embedding, and then we can go on to make the prediction. Once the model is trained, we can use it to predict the category of the new sentence by the first converting them into sentence vector by using the same word embeddings and then feeding them into model for classification. So that's how the classification can happen. In this example, word embeddings are used for feature extraction by representing text data in dense continuous vectors in low dimension, small number of dimensions space. Here we have seen 3 dimensions. These embeddings capture semantic, the meaning, and syntactic, the sounding, similarity between the words, allowing the classification model to effectively learn patterns and relationship in the text data for natural classification. Right? Make sense? Good. So what do we do next? So having looked at how to extract the meaning from the text data, we will now look at how to do image feature extraction. What are these image feature extraction algorithm and how can they help you? How can you use them to extract the features? So thank you so much for watching this third data collection and pre-processing lecture in this course, Master in Artificial Intelligence. I hope you're continuing to learn new things, continuing to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions and also download the PDF file to take a look at anything that we have talked about in greater detail. And do stay connected and come back to continue our journey into this feature extraction using image in the next lecture.